Okay, in this video we are going to look at the hybridization of the central atom phosphorus in PBr5. So the first thing we need to do when we're doing these types of problems is to draw the Lewis structure. So let's begin by drawing the Lewis structure. And we know how to do this, so we look at the valence electrons in the molecule. So phosphorus has 5 valence electrons, and bromine has 7. And there are 5 of those, so 7 times 5. This gives us a total of 40 valence electrons. And once again, this is just from the periodic table and looking at the electron configuration. Okay, so let's draw the structure. So we know that phosphorus is going to be our central atom because it's the least electronegative. Once again, we can see this from the periodic table. And then we're going to have 5 bromines surrounding the phosphorus. So 1, 2, 3, 4, 5. Now the final thing we have to do is place our remaining electrons to make sure that we don't have any lone pairs on our central atom. So let's do that. So far we have 2, 4, 6, 8, 10. So we need 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. So we know that our phosphorus here in this molecule has 5 bonding pairs and 0 lone pairs. So the next thing we have to do is we're going to assign the geometry to our phosphorus, and we know how to do this as well. So we can simply look at the number of bonding pairs and the number of lone pairs, and we know that this geometry is trigonal bipyramidal. Trigonal bipyramidal. Meaning, so we have these 3 axial bromines that are kind of like the fidget spinner in the plane, or the equatorial ones, excuse me, and then the 2 axial ones that are above and below. And this is from table 10.1 in your textbook. So the remaining thing we have to do is to assign the hybridization. So let's assign the hybridization. There's also a table in your book, table 10.4, that shows you the different hybridizations that correspond to different geometries. And we can look at that table and determine that this molecule has sp3d hybridized orbitals. There are 1, 2, 3, 4, 5 of them, so there are 5 orbitals total. It's made up of 1, 2, 3, 4, 5 orbitals, so there are 5 of them. Remember the rule that the number of atomic orbitals always equals the number of hybridized orbitals. So that's how we assign the hybridization in the geometry. Now let's take a look at how these hybrid orbitals actually form and go into a little more detail. So here I'll draw some hybridized orbitals. So if we know we're looking at our ground state, what we're looking at so in our ground state here, for our phosphorus, we know that we have 3s2, 3p3, right? So here. And I'm going to draw everything that's doubly occupied in red, and you'll see in a moment. So we have a doubly occupied 3s state, we have singly occupied 3p states, and empty d orbitals for now. And this is, once again, for the ground state. Now phosphorus in the excited state, on the other hand, excited meaning one of these electrons gets promoted. So this is 3D once again. So let's look at our excited state. So in the excited state, what happens is this doubly occupied electron gets promoted so that it's in an orbital all on its own. So these electrons remain where they are, and this red electron from here gets promoted to the 3D state. So now we're in an excited state. And what happens here is that these are the orbitals that combine to make our hybridized orbitals. So now we have 1, 2, 3, 4. So these are our sp3d orbitals, all with the same energy. And then we have left over these empty d states as well. So 1, 2, 3, 3d. Once again, these are empty. And this is going to look like so. So we have an electron in each one of these hybridized states. So these are the hybridized orbitals. And we have these empty 3D states that can also form bonds. So this is the way to think of the electron configuration of the phosphorus in our molecule.